part, I want to sort of look at determinants today, okay, and perhaps on Thursday as well. But what I want to do is first start on a determinant of a 2 by 2 matrix, and then determinant of a 3 by 3, and so on in the second hour. Determinant of a 2 by 2 is straightforward. Two things you should get out of it. You get, when you work out the determinant, you get a number. Okay, you get a number, you get a scalar, you do not get another matrix. So if you work out the determinant and you've got a matrix, you've gone wrong somewhere. Okay, you should definitely have a number. Okay, you should have a scalar. And I want to look at the geometric interpretation of what we mean by a determinant. One of the first persons was a Japanese mathematician called Seki. Okay, he was actually a household servant, believe it or not. Okay, who came across this idea of a determinant. And then, you might have heard of, you must have heard of Lewis Carroll or Charles Dodgson, who wrote Alice in Wonderland. He was a mathematician, believe it or not, okay, at Oxford. He wrote a book on determinants and gave it to Queen Victoria. And the title of the book is called An Elementary Theory of Determinants. He was at, like I said, he was at Oxford, and he did one thing good, which I'm not willing to do. Because Oxford University was going through a financial crisis, he's willing to reduce his salary from £300 to £200. Okay, if someone asked me to reduce my salary, I'd say no way, I wouldn't want to, But that was one thing good. But he was not such a good person. He committed a crime, a heinous crime. You know what it was?
He passed on double yellows.
Sorry?
He passed on double yellows.
No, that's a minor thing. No. What do you think? What sin did he commit? It might be the norm in those days. I don't think it was, but it might have been.
Did he make a math error?
No, not a math error. Much more serious than that.
Oh, was this the guy who was at Oxford College and was friends with Lewis Carroll?
Sorry, who?
Is this something to do with Lewis Carroll?
We're talking about Lewis Carroll, yeah.
Oh,
Or Charles Dodgson. Yeah, we are. Yeah.
Wait, is he? Wait, you talking about the one that? Oh, never mind. The one that wrote Alice in Wonderland.
Yeah, that's right. Yes, he's a mathematician.
Didn't he smoke opium?
Well, he did as well. But it's much more serious than that.
Okay.
Yeah, he was a paedophile. Yeah, well known. I don't know if it's well known. There's a BBC documentary saying that he's a paedophile. Okay, if you Google that in, Charles Dodgson or Lewis Carroll, okay, and you'll find that there was a BBC documentary some years ago. Their reasoning is simple: is that there's some inappropriate photographs of Alice when she was 11 and the sisters, okay, and which I don't know, I suppose he took them or something, so that's what he's like I said, a lot of people don't know that. I didn't know that until I read this as well. When I was looking at the history of this, I go, oh, how interesting this is. So, but he was a mathematician after all. Like someone said to me, Shabina Ahmed some years ago, she goes, she said, how come mathematicians are all full of, these paedophiles, these murderers and rapists and all that? And the reason is simple. You know why? Why mathematics is full of all those? It's not actually full, but you know why? Why you come across so many interesting facts about mathematicians. You wouldn't come across a computer science. Why not? Think about it. It's such an old history. Mathematics is old history. 2, 3, 4, 5,000 years. You're bound to find some people, aren't you? You're bound to find, whatever 0.3% of that population is bound to be either murderer, rapist, or whatever, aren't they? There's bound to be, okay? Computer science is a new subject, 30 years old, 50 years old, or whatever. That's why you're not going to find anything in computer science. In mathematics, you're bound to, simply it's such an old subject, okay? So you're going to come across your average or your 0.03% of,
See, you're not saying there's like lots of, you're saying ancient history. You're not saying there's lots of modern.
No, I'm not saying that. No way am I saying that. No. Okay, let's go into the determinant. Now, what do we mean by the determinant? Like I say, what you should get is a scalar. You should work out the determinant of a matrix, okay, and you should end up with a scalar. Okay, you should end up with a number like 3 or 4 or 5 or 0 or whatever, or -3, -4, -5. Okay, and that is will tell you what it will tell you is if you can find the inverse or not. You find the determinant of a matrix first, and that will tell you if you can find the inverse or not of a matrix. If you've got an inverse, then for a linear system like ax is equal to b will then imply a unique solution. Okay, if you've got the inverse, if you've got an A-1, okay, then you've got a unique solution clearly. So it tells you something. The determinant is like a pregnancy test. Okay, it tells you you've got inverse or you haven't got inverse. That's what it does. That's not my word. There was someone who read the book for me who said that, who made that analogy. I thought it was quite a good analogy. So how do we find the determinant? First thing is, you're currently finding determinant of a square matrix. So what I've done before in previous years, I said find the determinant of this rectangular matrix, and students have gone ahead and done it. You should say no, it's impossible. There is no determinant of a rectangular matrix. So look at previous exam questions, and you'll find I've asked students to find the determinant of a non-square, like a rectangular matrix, and students have gone ahead and done it. Don't know how they've done it, but they should, for 2 or 3 marks, they should have said it's impossible. That's what they should say. Or you can't, it's not a square matrix. That's what they would give a reason why they can't find the determinant. So what we're going to do is first find the inverse of, the determinant of a 2 by 2 matrix, and then the next section, or second hour, we'll do it 3 by 3. And like I said, this is why I highlight this point. You're going to find the determinant of a square matrix. Well, the determinant of a 2 by 2 is normally given by this formula here. How do you read that? How does it work? Determinant of A, B, C, D, okay, is given by AD, okay, AD minus BC. Leading diagonal, take away the entries on the other diagonal, okay. The product of the leading diagonal, which is this way, okay, and take away the product of the other diagonal. So let's do an example. Find the determinant of this matrix here, B, which is 2, 0, 3, 4. So solution to example 1, determinant of 2, 0, 3, 4. How do we find that determinant? Yep, go ahead.
2 times 4.
Yep, it'd be 2 times 4, yep. 2 times 4.
Minus 3 times 0.
3 times 0, 0 times 3, which gives you an answer of 8, doesn't it? Yeah? Okay, 2 4s are 8. Minus 0. Okay, so like I said, you should end up with a scalar. You should end up with a number like 8. This is what we'll end up with. You should end up with a matrix. You definitely should end up with a matrix. Okay, let's have a look at what does this actually mean. What does this mean when you get an answer of 8? What does it actually mean in relation to this matrix? How do we decide? Well, one, if we look at transformations, okay, and if we what do you call it? Multiply a rectangle. Sorry, no, not a rectangle. A triangle by this matrix. There's a triangle is given by the 4 vertices. So if I work out B0 or BA, okay, solution to BA. Solution to BA, okay? Now B is my matrix. B is my matrix 2, 0, 3, 4. And A represents the triangle, which is 0, 0, 2, 0, and 0, 3. Okay? Work that out. What do we get? If you carry out that multiplication, BA, what do you get? So yeah, it's 2 times 0, 0. Firstly, can we carry out the multiplication? Can we carry out this multiplication? Yes or no? Yes, we can. And the number of columns is number of rows are equal, so we can. So this is called P. Is it PQR? Yeah, PQR. So P dashed will be 0, yeah, and 0. Q dashed, okay. 2, yes, 4, yeah, 4, okay. And R dashed is going to be 0. Sorry?
I mean, we can't see it.
Okay. All right. So, what about this fifth entry? What's that? It's going to be 3 times 2, yeah? 4 times 0, isn't it? Yeah? Okay. 3 times 2 is 6, so that's 6. And then it's 12, isn't it? Yeah? Okay. So, if you take a rectangle like this, it transforms, this matrix transforms that into this, well, whatever shape it is. Looks like a rectangle, but let's have a look. If we look at the shape, what we get is this. what we get is something like that. So that's your initial PQR, and then you apply matrix B to it, and you end up there, you know, P dashed, Q dashed, R dashed, yeah? Okay, so let's have, what I want you to do is look at the area. Look at the area of the first initial triangle. What's the area of the initial triangle? If we take, what's the area of this triangle here? Area of triangle PQR. What is that equal to? You already tell me that. Come on, you is it? Are you all telling me you don't know what the area of triangle is? Sorry. That triangle, the shaded one. Could be 3, yeah. It's 2 times 3, isn't it? Yeah. Half of that, isn't it? 2 times 3, half of that. That looks like 3, doesn't it? Yeah.
Yeah.
Okay. 2 times 3 is 6. Half of 6, of course, is 3. What's the area of the triangle? Area of triangle P dashed, Q dashed, R dashed. What's that equal to? The large triangle now. Well, this is, if you take this to be the base, that to be the height, what do you get? 24 looks okay. 12 times 4 and half of 12 times 4, isn't it? Yeah? Okay. Half of, that looks like half of 48, okay? Which of course is 24. Now, can you see a relationship? Well, note this. The area, how's the area been increased? Area has been increased by what amount? By what amount? Yes, by 24 divided by 3, which is 8. And guess what 8 is? Sorry, Rachel, yeah. Sorry? Yeah, it's determinant of B, isn't it? Yeah. Okay, 8 is no coincidence, it's 8. Okay, determinant of B was 10, it'll be increased the scale factor by 10. If it was 1 over 10, it'll decrease the area by, you know, by 10, by a factor of 10. Okay, so the determinant is like, for a 2 by 2, is what we call the area scale factor. Okay, it's the area scale factor. You'll find that this is, you know, this is also equal to the determinant of B. Okay, let's take another shape. Let's take a unit square. So we've got an area of 1, because 1 is, you're something, you know, 24 divided by 1 gives you 24. It's easier to look at square rather than a rectangle. That's why I'm choosing this unit square. Okay, you look at this unit square, and if we apply that matrix to it, 3, 1, 1, 4, this is where we end up with. This is where we end up with. Okay, if you take this, you end up there. Okay, so unit square, of course, is got an area of 1. If you look at the geometric transformation of this, this is what you get. Okay, unit square goes to an area of 11. That parallelogram is an area. You can work it out by looking at the triangle. I'm not going to just assume the area is 11 for the time being. Work out in your own time. Okay, I haven't done this bit, but you should be able to do that by dividing up into, if you don't know the area, by looking at triangles and so on. And guess what? So this matrix, we applied this matrix to that. We applied that matrix to that unit square, and we ended up there. That's where we ended up with. We ended up with this. Okay. And guess what the determinant of that matrix is going to be? What do you think it is? What's your prediction? Well, we'll show it. What do you think? What's going to be the determinant of that matrix? Without working it out, go on.
Is it 11?
It looks like it's going to be 11. Let's work it out, shall we? Yeah. Let's see if it is 11. Okay. Let's see the determinant of. Okay, of this is 11. So determinant of A, which is 3114, is equal to, is what? So that's 4 there. What do we get? How do we work a determinant of 2 by 2? How do we work a determinant of 2 by 2? Sorry? Yeah. One diagonal, 3 times 4, okay? Minus the other diagonal, isn't it? Yeah? Minus 1 times 1, which is, of course, 12 minus 1, which, of course, is 11. And we, like, you know, we predicted before, it was bound to be 11, okay? That determines whether the determinant gives you the area scale factor. And doesn't just work, okay, you might say, well, this might be just a coincidence. It just works for those, you know, this works for those ones, okay? What I'm going to do is do it for a general matrix, A, B, C, D. If you do it for A, B, C, D, then you've done the whole lot, haven't you? Yeah? Any number. So it's not just those two, one with a triangle and the one with a unit square. It works for any, you apply a matrix A to some shape, okay? And the new shape, whatever it is, will be an area scale factor of the original function, or the original, shape. If you do this, this is where you end up with, okay? You end up with that. So a unit, take the unit square again. We want area of 1. 1 is good. When you divide by 1, you get the same number. That's the sole reason. You find lots of books use a unit square. The only reason they use a unit square is you've got area of 1. No other reason. They could use something else. But it's much easier to deal with, that you don't get lost in the arithmetic. And if you work out this area here, this comes to, guess what? It comes to AD minus BC, which is the determinant of the matrix. Okay, you can work out the area of that shape and you'll find it's AD minus BC, and that is the determinant of A, clearly. And of course, the area scale factor, when you divide by 1, you're going to get AD minus BC, clearly, aren't you? Okay, it may change the shape. You may get a different shape. You may go from a square to a triangle as well, okay? Okay, what about if, say if you've got determinant of 1, what would that mean? Say if you worked out the determinant of a matrix, then you've got determinant of 1, just 2 by 2, you've got determinant of 1. What would that mean in relation to transformations? So you've got determinant and you worked it out of a matrix. You've got 1, yep. Doesn't change the area, does it? It's not going to change the area. The area is going to remain the same. Does it tell you that's going to remain fixed? If you get a square here, yeah? If you apply a matrix with a determinant of 1, is it going to remain there or not? Or could it move somewhere else? Of course it could be very somewhere else, couldn't it? You could rotate it, couldn't you? For a start, you could translate it, couldn't you? You could move it left by 2 units and move it up by 3 units or whatever, couldn't you? Same area, isn't it? You could do that, couldn't you? Okay, so it's not just because you've got determinant of 1 doesn't mean it remains fixed, the same position. Okay, so for example, a rotation will definitely have a determinant of 1. If you look at a matrix which represents a rotation, you rotate that by 180 degrees this way. Okay, still have an area of 1, clearly same shape. Okay, so that are okay. What about a negative determinant? What do you think that means? What do you mean by a negative determinant? Say you've got a negative determinant. So we know what determinant of 1 means. What do we mean by a negative determinant? Yep.
Perhaps you're flipping the points.
Yes, that's it. Well done. So, I suppose you haven't done linear algebra, but yes, you are flipping the point. That's what's happening. You're changing the orientation of the area. So, for example, if you've got this shape here, okay, or the original shape, okay, a positive determinant is that one there. It's more or less the same. You're not really flipping the points. Okay. Here, look where AB is down here. Okay. Hang on. This should be D, and this should be B. Is that how it's in the book? Can you have a look?
Yeah.
Yeah, sorry, that's wrong. I didn't realise. So you're flip, like you said, like Rome just said, you're flipping it over, okay? You're turning it the other way, yeah? So this is your red vector, goes down here, and your blue vector comes up here, okay? You're flipping them over. Okay, so a negative, determinant will say you change the orientation of the area. That's what you do. That's what it means. So if you find the determinant of UV, that should be, same as the determinant of VU, but it's a minus in there. If I ask you to find the determinant of UV and you find it, 2 vectors U and V, okay, you get an answer of 5. If I ask you to find the determinant of, VU, V first, then U afterwards, it should be minus 5. It's got to be minus 5. Okay, so for example, here it is. If you've got A represents 2 matrices UV, okay, 2 vectors is positive. You swap those vectors over, okay, then that should be negative of that value. Definitely going to be negative. That's positive, 100%. Okay, let's do this example here. Let's evaluate AB. Okay, the multiplication of AB. Let's see what do you notice about your results. So A, okay, A is equal to A, B, C, D. Okay, and then you times by B, which is AB is equal to 1 over det A times by D minus B minus CA. Okay, what do we get? How would you carry out this multiplication? What's the obvious thing to do? Yep.
And the determinant?
No. You might have to. You might have to. But something else, something more obvious to do. What's that? If you don't do that, you're making your arithmetic life a lot harder. Bit like integration. You know, if you don't take if you don't do certain things in integration, similarly, if you don't take one elementary step, you're making life really hard. Well, not really hard, but you're making it more difficult. Why make life? Like I say, always ask your question. Can I make this easier? Always ask your question. In every calculation, you should do that. Yep. Yeah, put that on the outside. Yeah, put that in the front or put that in the back or somewhere. Yeah, park that to one side. Yeah. What I would do is not get in your way. You don't want to divide. I don't want to divide. Okay. Park that right at the front. So 1 over det A is at the front, and then carry out this multiplication A B C D. Okay. D minus B minus C A. Okay, let's have a look. 1 over det A. If we want to multiply this, what do we get? What's the first entry going to be? Yep.
AD.
Yep.
Then it'd be minus BC.
Yes, of course. AD minus BC. AD minus BC. Correct. Second entry here, I mean. Let's have someone else. Is Tafiq not around? He's not around. Another one likes to answer questions. You should never answer questions now. I know he's absent. Come on, what's the second entry? I can't believe Patrick's the only person who knows that. What is the second entry?
CD minus
CD?
CD.
No. Second here. Oh, there, yeah. CD minus CD, yeah, down here it is, you're right. And what is that? What's CD minus CD? 0. Yeah, sorry, yes, I meant here. Okay, yes, you're right. That entry is CD minus CD, which is 0, clearly. The entry here, I'm talking about, what this one here? Sorry? Minus AB, yeah. Yeah, minus AB plus AB, which gives you 0, yeah, 0, okay. What do we have at the last entry? Sorry? Yeah, AD minus BC, okay? AD minus BC. AD minus BC. And what could you do with that? What could you do with that? Yep.
You work out the determinant. So then you could just...
Well, the determinant of A is... Yeah, all right. Is determinant of... is AD minus BC, isn't it? Yeah?
Yeah. Okay.
So AD minus BC, 0, 0. AD minus BC. What do you do? What can you do now? Take out a factor or take it in, whichever way you want to do it. Either one will do, wouldn't it? Yeah. What do you end up with if you carry out? If you take the AD minus BC out, or you take that in, what do you end up with? Identity. Don't you? You end up with 1, 0, 0, 1. Yeah. Okay, that's what you end up with. Okay, and that's important. So if you carry out this operation A times B, you end up with 1, 0, 0, 1, the identity matrix. So what can you say about A and B then, if you end up with the identity matrix? What can you... Yeah, go on, Rachel. Yeah, they're inverses, aren't they? The inverse of A must be B. It's got to be, because A times B gives you identity. You know, if I tell you X times Y is equal to 1, Y must be the inverse of X, mustn't it? Okay, so we know, hence, A minus 1 is equal to B, which is 1 over the determinant of A times D minus B minus C A. Yeah, that's going to be, it's got to, sorry, you can't see. It's got to be that, doesn't it? You've got no choice. It's got to be, here it is. Here it is. Okay, so
we can't see.
Okay, hang on. Let's use this one here. There it is. The determinant, the inverse, is given by that, yeah? That's got to be the inverse, doesn't it, yeah? But why doesn't it work? Why do I have to have this provided det A is not 0? Yep.
Because you don't know what A and B...
No, I'm saying, why is there a qualification... go on, you, Poker. Yeah, 1 over 0 is not defined, is it? Yeah?
Okay, yeah.
Okay, so if you do, you're ending with dividing by 0. Okay, so provided you can find the inverse, provided the det A is not 0. Okay, if det A is 0, you're going to have problems. Well, we'll see what that means in a second. Okay. So really what it means that now you know how to find the inverse of a matrix. It's given by that formula there. It's not in the maths handbook, you've got to learn it, okay? So how do you find the inverse of a matrix of a 2 by 2? It's straightforward, like I say. Much easier to learn this one than the 3 by 3. What do? There's A. So what does it say? What's the inverse? How's the inverse given by? Come on, should know. Can't you decode that for me? There's A, B, C, D. So find the inverse. What do? Yeah.
Well, you find the determinant of it. And
first, yes, that's true. Yeah.
Then you get what? Then you swap A and D around.
You swap A and D around. Yeah, look, A and D.
Minus B and C.
Yeah, minus and put minus on the other diagonal. Okay, that's what it means. And we know that works because when we worked out A times B, you worked out A times A. We get I, don't we? So it's got to be the inverse. Okay, it's got to be the inverse, or we wouldn't get I. Okay, so let's like I say, you could look at. I'm going to go on transformations because that's chapter 5, but I have used some of transformations here, but you don't need to know the transformations as such. What about det A? What about if det A is 0? What happens then? What can we say about when the determinant of A is 0? What does that mean? Yep.
Does that mean that we don't have a determinant?
We haven't got determinant. The determinant is 0. The determinant exists because the value is 0. But what does it tell you? What can you say? There's no inverse. Okay. If the determinant is 0, that means it's got no inverse. We've got no inverse for that. Okay. And why shouldn't we have an inverse? The natural question you're going to ask me is, well, why shouldn't we have an inverse for determinant A is 0? Well, if you apply to transformations, if you apply again, you apply the triangle we had at the first triangle that we had. Yeah. If you apply that, okay, that triangle. So you apply B to that triangle, you end up, there's the triangle, this is where you end up with. What's it done? Yep.
Has it made it into a straight line?
Yes, it has made a straight line. So what does it say? What's the area of the straight line? What's the area of the straight line? Have you been asked that question before? Area of a straight line. I mean, there's 3 students who do philosophy. What's the area of a straight line? Maybe I should ask you. More a question of philosophy than mathematics, I suppose. Come on, someone should have the confidence to say the answer.
What is 0?
0. Of course it's 0, isn't it? When have you been asked to find the area of a straight line? You've not been asked to find the area of a straight line. Have you ever been asked to find the area of a straight line? No, it's 0, isn't it? Okay, 0. And of course it makes sense. Because guess what? Guess what the determinant of this value, this is, determinant of B is going to be?
0.
It's going to be 0. It makes sense now, doesn't it? Yeah? You're going to get... So think of it. If you want to have the inverse, you've got to find a way from getting the straight line back to there, don't you? Inverse means you have to go back. You've got to go back to that triangle. And you can't move from a 2D space. When you move from 2D to 1D, you can't move back from 1D to 2D. That's the problem. Okay, you've got a straight line. Where's it going to go? Make it somewhere, make it to a square. Like where's the only way to go? Okay, you haven't got an area there. It's like a straight line. So you go, once you go from 2D to 1D, if you go lower dimension, then you have got no inverse. If the matrix transforms a vector or transforms any shape into a lower dimension, okay, it's going to have no inverse. And definitely no inverse. There's no way back. There's no way back from 1D to 2D. Okay, you go from 2D to 1D, yes, you can do that, but you can't go the other way. Okay? So this is going to have no area, and of course, if you work out the determinant of this, you'll find the determinant is 0, which confirms what we thought. The area is going to be 0 clearly. Okay, let's find the determinant of these let's find the inverses of these or the following matrices of A. How do we find the inverse of A then? How do I find the inverse of A? What do I need to do first? What's the first thing I should do? Let's have someone else. What's the first thing you should do? Come on. Be confident, you know. I've been telling the second years that the first years are a lot more vocal and a lot more interested to teach, and now you let me down. Yep. Yeah, find the determinant first. Why should you find the determinant first? I would definitely find the determinant first. Yeah, go on, Sophie. Yeah, see if it's got inverse. It might not have an inverse. Okay, so you don't waste your time trying to find an inverse when the determinant is 0 or something. Yeah. Okay. So that is wrong to write that down. I want to find determinant of A. Okay, which means the determinant of 2, 3, minus 1, and 5. What's that determinant? How do I work out that determinant? Come on. Yeah, it's 2 times 5, which is 10. Plus, yeah, well done. Plus 3, isn't it? Yeah, which of course is 13. So does it have an inverse? Yes or no?
Yeah.
Of course, non-zero. 13 is not 0, is it? So it's got to have an inverse. So now we can say A minus 1 is what? It's given by. What's? I'm going to give you the formula. What's A minus 1 given by? Come on, there's the formula. There's the formula. Come on, you tell me. Go on, Patrick. Tell us what it is.
So it's 1 divided by 13.
Yep, 1 divided by 13. Yep.
Then it'll be 5.
5, yes. Let's just chop them around, shall we? 5 and 2. That's what you've done, haven't you? Yeah. Go ahead.
And that would be minus 3.
Yeah, minus 3. That's right.
Oh,
Yeah. Minus 3. Yep.
Then 1.
Yeah, plus 1, isn't it? Yeah. That's your inverse. There it is. There's your inverse. Swap the leading diagonals and put minuses along the other diagonal. That is your inverse. Okay. All right. Let's do this one here. Down to of B. So you just shut up. B. Again, how do you find the determinant of this matrix here? What's the first thing you want to do? You find the determinant. So determinant of B is equal to the determinant of root 2, 1, 1, root 2, which is given by what?
Minus 1.
Oh, yes, well done. Good, thanks. Yep, minus 1. What do we get? Come on. Yeah, 2. Root 2 times root 2 gives you 2, doesn't it? Yeah? 2. Yeah, plus 1, which of course is 3, isn't it? So has it got an inverse, yes or no? Yeah, of course it's got an inverse. Clearly it's non-zero, isn't it? So B, the inverse, is given by what? What's the inverse given by? Yeah, 1 over 3. That's right. 1 over 3. Yeah, root 2 change root 2 is root 2, isn't it? Yeah, they're going to be the same number there. Root 2, yep. Minus 1 and plus 1. Yeah, that's it. That's your inverse. Okay, for that. What about C? What about C? How do you know there's no inverse? Shall we check that? I think you're going to be right. But, how do I know there's no inverse? Yeah, it's pi squared minus pi squared. Okay. If you work out the determinant of C, it's going to be pi squared. Okay. Minus pi squared, which of course is 0. So that means no inverse. Okay, you should have no inverse for C. Okay, clearly it's going to have no inverse. Something you come across in differential equations is what's called the Wronskian matrix. Okay, the Wronskian is given by, if you do differential equations in your second year, okay, you've got to find if the solutions are independent or not. And the way the Wronskian works, a Polish mathematician, okay, it is Wronskian of two functions f and g is given by fx, gx, okay, and then the derivatives, the determinant of the derivatives beneath them. Yeah, so let's work out the Wronskian. Let's work out the Wronskian of cos. So the Wronskian of cos x sin x, or w of cos x and sin x is equal to what? Well, it's determinant, isn't it? Yeah, it's the determinant. So it's the determinant of what? Because it's an important determinant in differential equations. Can't we just use that formula there? What's going to be what's f? Cos x, yeah. So it's cos x, okay? That's cos x. And what's g? Sin x, yeah? Okay? So sin x. Okay, and then what do we have underneath? Yep.
Minus sin x.
Yeah, you differentiate that, don't you? Cos, which is minus sin x.
Then you've got cos x.
Then you get cos x. Yeah, exactly, cos x. How do you find the determinant of this matrix? Those have got numbers in it. The rules are not suddenly, like I say, the rules of mathematics are universal. It doesn't say that you can't apply this when the entries are functions, does it? Yeah, cos times cos is one diagonal is cos squared x. Yeah, plus sine squared x, which is equal to 1. So the determinant of that is equal to 1. And that, if it's not 0, that means you've got two independent solutions. Okay, so when you have when we do differential equation, which we will start in MT1, I'll take you for that in a couple of weeks' time. You'll find that we sort of hand wave the same. We've got two solutions. Okay, but you need to see they're independent. They're different solutions, not the same solution. And so what we want is the inverse of a 2 by 2 is given by that, provided that determinant is not equal to 0. Yeah, determinant of is not equal to 0. Any questions? And this will happen. Any questions? No? Okay, let's go on to determinant of other matrices. Sorry, I was telling Patrick, this is pink paper. This was, and I didn't know someone else put this pink paper in, so I had no choice to look at this to use.